is the biggest thing you need to be concerned about, is how to visualize an individual molecule. So we've got the issues with sigma bond rotations, and then we get different viewpoints on a structure as well, and that's where we got our Newman projections. So if we were, and then also our chairs. Okay, so if we were gonna, okay, so if we were gonna look at a chair to try and understand something about the energetics of why a chair might be more stable than another, we would have to change our viewpoint on that cyclohexane to get to the point where we could see the Newman projection. Okay? And it turns out that we can still use Newman projections, but it is two Newman projections aligned next to each other. Okay? So if we look at the chair shown on the left, we've got the eyeballs looking down. Right? That's what we would end up visualizing. So if we look at our drawing here, that carbon is below our seat, so that's kind of our feet placement. That little thingy is going to irritate me. I'll fix that later. And if we look to our Newman projection, that is this carbon. Okay, it's the feet of our chair. The head, or where we'd put our head, is in the back. That's that head carbon. Okay, so what we're doing is visualizing and disappearing the bonds kind of in between, which, I don't know if you can see those, but those purple lines are now the Newman projection bonds. That's how we're visualizing down at this. Okay? Yes?
How does this work if it's not a carbon? So
the exact same way. If it's not a carbon, you can do the exact same thing with it. You have to add that information in. It would get a bit messy, but you could go through and do it. Let's just take a look at the Newman. We just said put a nitrogen there. We're going to get the same result. Okay. It is typically not used for that because it does get a lot messier. You'd have to add that detail into it. And so you typically only see Newmans done with carbons.
All right.
Okay. You can drop in other atoms, but it's messy.
I was just wondering as far as notation goes and how that would look.
Yeah, it's going to look messy.
Okay.
Okay. So the whole point behind this is to really kind of get a different view on the bonds or the potential substituents coming off of the chair. Because what we're talking about in the next stage is recognizing what happens if we do a chair flip. Okay? And this is where things get a little bit weird. And of course, I don't have a model built. Looks like someone's taking apart a model, so that doesn't quite work. So we'll see what happens here in a second. If we looked at the pen as kind of an example for doing a chair flip, okay, the most common response students do is, well, I'm going to draw a chair flip. And they take the pen and they flip it over. That is not a chair flip. I know that sounds like a flip, but that's not what we're talking about with a flip. What we're talking about is actually rotating the bonds. Okay? And with the pen, you're like, well, but that doesn't look any different. You're right. With the pen, it doesn't look any different. With the chair, it does. Okay? So if I'm going to undergo a chair flip with this, what are we talking about doing? Okay? If I do a chair flip with this structure, what was my head needs to get pulled down to become feet, or where I would put my feet. What was my old feet needs to get pulled up to become the head. Okay? The result of this is that the chair changes the direction of its alignment. Okay? If I sat in this chair, I'd now face this direction. If I sat in the original, I'd face that way. We're changing the viewing direction. Okay? The reason this is so important is that if we evaluate what happens to each of the bonds coming off of the ring, we notice some kind of stark differences. Okay? And that really stands out in our Newman projections. So if we took a new cyclohexane, okay, and we put two substituents on it. Okay, we've got these labeled as E and A. If we tried to convert that drawing into a chair, well, here, let's actually try that. Do that. Convert that drawing into a chair. Okay, see what you can come up with. So it was a bit rude because I drew it without telling you that I was drawing it, and I didn't actually record me drawing it. So there's our chair. Okay. Just in looking around at people, if we take a look at the upper right-hand corner, I see lots of chairs drawn like that. Those are bad chairs. Okay. That means you need practice drawing them. Okay. The reason for the practice isn't because you're supposed to become a better artist. These drawings are what you base your answers on. If your drawing is bad, you're going to have a hard time basing or coming to any real conclusions about those drawings, and you'll need to memorize the application of them. Okay? Yeah.
I think I drew it backwards, but is that E's coming out and A's going in?
So let's break this down. So I would argue I have a head in orange and I have my feet in purple. All right, this is going to be the easiest way for me to visualize this. Right? There are two ways that you could then take that Newman projection and rotate it so that you could get a chair. For me, I'm taking the head and I pulled it to the left. Okay? When I pulled that head to the left, I get that bottom structure. Okay? Which is insanely difficult to understand if we don't really see this. Remember, this is a three-dimensional model. That head atom is coming out of the plane, kind of above us. So what we're doing is grabbing a hold of that, and I'm now just pulling the whole structure to the left. I'm kind of pivoting around a center axis. Okay? When I do that, that head is now up at the left-hand side. The feet are now at the right-hand side. Okay? That equatorial E atom in my Newman projection is on which side of my chair? The E is on the left-hand side if I'm pulling that to the left. As I pull it to the left, what's going to happen? That E going out to the left is then going to go, it's going to go and face away from me. So it's going to be on the back side of the chair. Okay? All of this stuff is behind the plane of the paper. Okay, you'll never see it with dashes drawn on it because it just looks weird and awful and ugly, but that's behind the plane of the paper. Okay? The A atom being on the right-hand side of the structure, sticking out to the right, if I turn that head and grab and turn it, it's now coming out towards you. Okay, so that A then needs to be out in front, which means all of these are now wedged coming out of the plane. Which then kind of begs the question, what's in the plane of the paper? A is not in the plane of the paper. A is attached to an atom that is in front of the plane of the paper. So by definition, A cannot be in the plane of the paper. The head and the feet are the only two atoms in a chair that are ever in the plane of the paper. Everything else is outside of the paper. Okay? If you had those weird, goofy kind of bow tie structures for your chairs, that becomes very difficult to interpret where those wedges and dashes and everything is aligned, which makes it difficult to interpret a drawing like that. Okay? So the better we can draw our chairs, the better we can come to those interpretations with where the atoms are located. We will encounter another issue in how we represent those. Okay? So in this case, you'll notice I drew the A where? Straight line, straight down on the plane of the paper. Okay? Or sort of looking like it's in the plane of the paper, but straight down from the structure. The equatorial one? So we're hearing a couple things. One is straight up. I'm arguing it's not exactly straight up, right? It's got a little bit of a tilt to it. Like, that's just subtle nonsense. That subtle nonsense is actually meaning I did that intentionally. Okay? The equatorial atom, if I look at it, isn't aimed straight up or down, is it? In the Newman projection, it's kind of aimed straight out to the side. How could I draw straight out to the side on the chair? I could add dashes on top of that's going to be really hard to see. Okay, so I have to come up with some way to differentiate those. The A atom is straight up and down. That one, okay, straight up and down. That E one, not so clean. Okay? So let's add a little bit more information into this because maybe this will help visualize it. So there's that E atom. Let's draw in this H. Where's that H? Well, it's connected to the exact same carbon that the E is. And where is it? Straight up and down. There's my H. Anybody notice anything kind of interesting about where that H is aimed? It's like the A. Yeah. Should it be like the A?
Yes.
A is aimed straight down there. The H is aimed straight down on the other position. Yeah, it should be aimed exactly the same. If there was any kind of difference there, we're now showing a difference between those structures. If we did the same thing with the hydrogen on the other one, okay, where is that hydrogen? Okay, well, it's not aimed straight down. It's kind of off to the side. It's kind of off out here. And that's how that one gets drawn on. Okay? So there's a difference between those positions and how we represent them. Those ones that look like they're straight up and down, in our chairs we try and draw straight up and down. Straight up and down from what? Because remember, doesn't that E, we get some people saying, well, that E is straight up. That's supposed to be different than the A. It is different. If we look at where the A is connected, there's kind of a little triangle arrowhead point, right? Everybody see that? Where's that little triangle arrowhead point largely aiming? So some people are saying up. If I stabbed you with that arrowhead point, is it going to hurt you on the upward direction? No, where's it going to hurt you? The arrowhead is aimed largely down. The A needs to be aimed straight down from that. If we look at the other one, because that hydrogen, that red hydrogen, is the same kind of orientation as the A, look at its triangle point. Where's that triangle point aimed? Same deal, down. So I'm going to aim that one straight down. Okay? The other two positions aren't aimed straight up and down. They're aimed out from the structure. Those become difficult to draw. The blue hydrogen, not that bad to draw. Nice and easy away. That E, not so easy to draw. That's like trying to draw where my arm is three-dimensionally. Okay? The right arm, the one that's harder for you to draw. Okay? Since it's going kind of backwards behind me, that's a little bit more challenging to deal with. Okay? So we just kind of invent a way to draw that, and this is the invention that we came up with. Okay? So the red E and the blue H, okay, will be drawn opposite directions of that stabby point. Okay, so the red E is aimed in the upward direction, away from the stabby point. That's to represent that it's coming out from the structure, not up and down. Kind of, sort of? Yeah.
Is it the E's on the left side?
The E is on the left side in our Newman projection, but remember what did we do? We took that head, and I grabbed it and I pulled it where? Where's the E aimed now? It's now behind the plane of the paper. That's why it's on that back one. Okay? All we've done is converted a Newman projection into the chair. We haven't even gotten to the hard part yet, which was doing a chair flip. And in the chair flip, I have to somehow convert this by doing single bond rotations. If you have a model kit, you now need to do that. You need to take what was the feet, those purple feet, and pull them up to become a head. What was the head, that orange atom, you need to pull down to become the feet, to change the direction of your chair. And I can't believe I goofed with that stupid logo in the way, which is really bothering me. So I'm going to have to, I can't erase it. I have to change rights, copyright things. So what happened is I took that purple atom and it's now a head. An orange atom is now feet. There's my chair. Okay. Let's call this, can everybody see the purple line? Wedged or dashed? Dashed, good. Those people laughing probably didn't see it as dashed. Okay? It's not easy to nail these down, but that is dashed. That's still behind the plane. Okay? The wedged orange ones now are coming out in front. Okay? Those are all in front of the plane. Okay? Where's that blue A located? It's on the carbon in front of the orange. Where's the carbon in front of the orange head? Right there. Okay? And it's all about that weird, because it looks like it's twisted. This structure is not twisted. That's the hardest thing with this. We have a very subtle flip in this. And all of a sudden, when we look at our drawing, it looks like our structure is twisted. It hasn't twisted at all. It's identical. Okay? For those of you that have the model kit, is your A aimed straight down anymore? It's to the side. Okay? So it's not even the A straight up. I can't go straight up from that position. Okay? So it is going to be there, and I'm going to have these two kind of bonds chilling out there. And we're going to say, well, the A was straight up and down, so it should still be straight up and down. Remember, we didn't flip the structure. We just did a rotation, which means A is still in its same relative spot. Relative to the ring, A is aimed downish, which means when I do the chair flip, it still needs to be aimed downish. Which of those two blue lines is downish? Well, the down one. Yeah, sorry. That was kind of bad. But, hey, there it is. A. Okay? And our hydrogen's up there.
So the A isn't going straight down, it's going down to the slant.
The A isn't going straight down anymore. For those of you with the model kit, where was it going? Because I heard a couple people say it. It's going out to the sides. Okay? If we looked at it, it's almost coming straight at you in the model. There's no way to draw it coming straight at you nicely on the drawing. So we have it kind of with that slope down so that we can see that. Okay? Notice again, our triangle point there is aiming where? Up. A's no longer following the triangle point. It's changed its relative position. Okay? Where's the E atom connected? Okay. Dashed carbon. Our E atom is connected here. So it's either this line or this line. First one, the one aimed up. And the hydrogen, now aimed to the side. Still aimed down. If we take a look at our first drawing, the hydrogen is still aimed down. Still aimed down. Okay, we're not flipping the structure over. We're just doing a sigma bond rotation. That internal sigma, and it turns out it's like every sigma bond in your ring rotates. Okay? The reason this becomes important, this E atom is now aimed straight up and down. Where was it aimed in this drawing? To the side. The blue axial atom and the blue A atom, and they're both goofy. The more colorful drawing is aimed to the side. The blue A atom in our initial drawing, straight up and down. Right? In those views, it doesn't look obvious that differential. Right? We might see it, we might not. This is where the Newman projection has power. Because if we now keep our view on the exact same system, okay? Oh, that was probably the wrong way to draw an eyeball. If we now look down those, and my drawing's going to disappear here in a second, so it's okay, because we're maintaining the same viewpoint on our structure, we could end up with a new Newman projection. Right? What happened? So again, we took our orange head, and what did I do? Pulled it down to make feet. There's the orange head, now below the plane of the seat, because that's where my feet typically are. Okay? What happened to the purple, the old purple feet? We pulled those up to become a new head. Right? What happens to the E and A atoms? Well, if we take a look at the E one, what happens? As I do that rotation, it swings up. Right? Because I find that confusing. I'm going to get rid of that. There's our E. What happened to the other one?
It swung down. Or up, I guess it's kind of.
It still swings up a little bit. It's still aimed down. And there it is. Right? Does it look like there's now a distinct difference between those two positions? Can I make the argument that A has the same energy as E in this Newman projection? No, they're Newman projections, so what should I be looking for? Staggered conformations, which only really work for ethane. So instead of staggered, I should be looking for gauche and anti. The eclipsed, we're not going to see here because these are staggered conformations for our chair. And if we went through to try and evaluate these, we should be seeing a gauche interaction here. To that exact same position, we have an anti. Which is more stable? Anti. So given the choice, which of those would I prefer to have? Do I want the E or do I want the A? I want E. E is now going to be more stable because it's as far away from that ring as possible. So that E position is more stable. So go, okay, well that's good. We could now reference that as a different position. That E position I can now name, because it's kind of going out from the sides of the structure, as equatorial or equatorial. I don't care how you pronounce it. The A1 going vertically is kind of on the axis of the molecule. Right? And yes, I'm fully aware we've got axes all which ways, but that's how it sticks in my head. Right? So we have A for axial and E for equatorial. So we might say, well, just put everything in the equatorial position and all is good. But remember what happens when we do a chair flip. What happened to E when I did a chair flip?
Axial.
It became axial.
Wait, so the chair flip, are we turning it this way or turning it?
So, and again, this is the confusion. And I totally can't do this. Oh, here we go. We got a model kit. Awesome. So, number one, need to be in a chair. Am I in a chair?
No.
What am I in? On the rocky seas. A house? It's a boat. This is the problem with naming shapes. We're in the boat. Okay, there's our boat. So that would be a very awkward chair to sit in. Both your head and your feet are up. So now I have a chair. Everybody kind of see it? Okay, so chair flips, because we got the model, so thank you. Let's go ahead and address this again.
No.
Not a chair flip. Not a chair flip. Chair flip. Nothing up my sleeves. Head and feet, those are the only two atoms I'm holding on to. This is one of the reasons why, by the way, I like this model kit. If you try and do this with any of the other model kits, it's not as easy to do the chair flip on. Take the head and I want it to become feet. Notice as I did that, what happened? They rotated. Well, what rotated? The sigma bonds are doing a rotation. That's what's causing this. And I rotate the other one up. We now have a chair flip. My hands, when I go through the chair flip, are in the exact same position. It's just either up or down.
So those 4 carbons stay in the plane.
The 4 carbons of the seat stay in the same plane. Okay, just the head and the feet exchange their relative positions. Why does that get misleading? If I sat in this chair, which way am I facing? So if I did a chair flip, now which way am I facing? Not a chair flip then? No, that was a structure rotation. Okay, so rotating the structure can make it look like the chair's changing directions. That's not a chair flip. The chair flip requires sigma bond rotation. Okay, this is not a sigma bond rotation. This is flipping the molecule. The bonds rotate. Okay, that is what we're trying to represent within these drawings, and that is not easy to do. That's why it causes problems. Okay, kind of, sort of.
Thank you. Yeah.
Okay. So what happens when we go through that chair flip? That position that we had labeled as equatorial, is it equatorial anymore?
Axial.
No, now it's aimed axial. Hence, I changed the label on it because it's no longer equatorial. I can't reference it as that. I've got the E in parentheses representing that was the former equatorial position. What happened to the other one? It became equatorial. So every time you do a chair flip, positions that are axial become equatorial. Positions that were axial become, I think I just said the same question twice. Positions that are equatorial become axial. So we exchange. Does that change the stability argument? The equatorial position is anti, which makes it more stable. If I go over to this structure, is my new equatorial still anti? Yes. Is my new axial still gauche?
Yes, it is.
Yes. So the relationship that equatorial is more stable than axial holds true regardless of the chair flip. Okay? All that changes is the relative energy of the structure. This is kind of similar to the arguments. We didn't really have arguments, but when we discussed it, looking at these two structures. Which one's more stable?
The one on the left.
The left. And that pause is telling, because to me what that pause is representing is that you aren't comfortable looking at this structure in a Newman projection. Because if we change our view and now look at these in a Newman projection, this is what happens. The structure on the left versus the structure on the right the structure on the right is eclipsed, and the structure on the right, or left, left,
Staggered.
is better referenced as anti, but we could also reference it as staggered. Okay? This all comes, that's a boat. This all comes from trying to represent these three-dimensional structures and be able to see those different energetics. Okay? That requires practice, and that largely requires practice with the model kits. Okay? The lab you're doing this week is exactly that, forcing you to use the model kits. Okay? If you're in the Wednesday lab section and you want that practice, talk to me, and what I'll do, in fact, you don't even need to talk to me. I will post the model kit activity to Canvas so you have access to it so you can see what's going on with it. Okay? If you're in the Wednesday lab and you want extra help, you can come into the lab today, okay, and get frustrated and irritated with playing with these model kits. Okay? A lot of people think the model kit lab doesn't take that long. It is one of the most frustrating labs for students to deal with. Okay? Because it's, can you see it? No? Keep looking. Okay? It takes a little bit of manipulation to get used to. Once you've got it unlocked, you can answer a lot of questions with that visualization. Is there a cheat? Yes. What? Axial is? Higher in energy. Equatorial is? Lower in energy. The more low energy I am, the more stable. The higher in energy, the less stable. You've answered the majority of questions that you could see, particularly in a multiple choice. Where things get a bit haywire is when we ask you to try and draw or represent these structures. Say like within here. Okay? So, you guys want to just try them immediately on your own, or do you want me to walk through one? Walk through. Okay. I'm only going to do one, and then I'll make you do another. Okay? So, first thing that you should notice in this kind of question, okay, is what are you trying to do?
You have to draw the two.
We want the lowest energy, so that was a good tip off. Low energy typically means equatorial. So when you go through to draw out your answer, where should you put your groups? In the equatorial positions. Okay? You can use the cheat. We know that's where they're supposed to be. Let's make them equatorial. Okay? There's another aspect of this question that usually trips students up. What's the other aspect? Nomenclature. You have to know where to place these things on those structures. We can't just say, well, everything goes equatorial. Because if I place everything equatorial, that may not be that compound. Okay? So there's two ways that we could view this structure. We can view it from an overhead view or from the chair. With my experience, I'd probably jump straight to the chair to try and evaluate it there, and then go back to the overhead. Okay, why? Lowest energy I see is harder. I see that being more apparent in the chair configuration. Okay? But that could be not you. Okay, so let's go through and look at the name with the overhead, because that's typically easier to process. Cyclo. We've got a ring, hex, 6 carbons, conveniently drawn for me. What isn't drawn for me?
Your two methyl groups.
The 2 methyl groups. Okay, so I need 2 methyl groups. Because it's a cyclo, I know I can put the first methyl group anywhere I want. I'm going to put it straight up. Now what? I need the second methyl group, which goes where?
Next to it.
On the carbon next to it, and I get a 1,2. This says cis, which means they have to be on the same side. For me personally, I think it's easier to draw in wedges, so I make them both wedged. Okay? So I'm responsible for being able to do that. The next part is how I overlay it into the chair. I could try and change the view on the molecule. I could have a model already built, which I'm going to highly recommend you do. Okay? That all you've got to do is build the overhead view, and now bam, there's my answer, I'm done. Okay? I would argue that is difficult, so what I'm going to do is jump to the chair, because I don't have a model kit in front of me, and use the information I know. Okay? I know it has to be cis. I know I need equatorial. So the very first substituent I'm going to put in is going to be a methyl group, and I'm going to put it in such a way that I can tell it is equatorial. So I'm going to put it right here at the corner, because that tends to be one of the easiest places to put things. You'll find these 3 spots are really easy to draw. These 4 purple ones are really hard. Okay? And actually, really, you could probably actually say that one's pretty easy. Okay? Which of those corners do you want to start with? What was that? The right top, I can accept that. If we look at that, there are 2 positions there. Where do I put the methyl? Okay. My equatorial is not the up-down one, which means I want my methyl here. CH3, and I could put an H there. Okay, now what do I got to do?
Neighboring carbon, you need to put an axial down and equatorial.
I need to put on another methyl group at the next position. That next position could be tricky, so we do have to be a little bit careful about this, and this starts to reference into chapter 5. Right? This CH3 that I just put on was which of those two CH3s up top? The first one, yeah. Thank you, Jed. The first one. Clearly. I'm going to call it that one. So when I get to the blue one, I'm moving which way around my ring?
Clockwise.
Clockwise. Where's the clockwise direction from the carbon in my chair?
The red dot.
The red dot, not the purple dot. Okay. Is that important?
Yes.
In this case, it isn't that big of a deal because everything's identical. In other cases, yeah, as soon as we move into chapter 5, that becomes incredibly important and you end up drawing the wrong structure. Right? So we want to go clockwise, so I want to put my blue methyl at the red dot. Because my answer said, I do see you, equatorial, I'm going to put the blue methyl equatorial. So there's my two positions, CH3 and H. Most common answer by students, which also happens to be wrong. The red methyl is aimed where? Down. The blue methyl is aimed up. What did I just draw? Trans. I wasn't asked for trans. I was asked for cis, which means? It would have to be drawn down. Okay? I see something that I want to fix here in a second. We'll address that in a second. First, your question.
Do you have to number the carbons? Is there a specific way you do it?
As far as numbering the carbons, there's no specific way to do it as long as you go in sequence and consistent. If I count clockwise, I count clockwise. You can't switch and start going counterclockwise when you draw a new structure. Okay? So if you want to number counterclockwise, 1, 2, 3, 4, 5, 6, that's fine. Just make sure every time you go counterclockwise. Okay?
Why is this the right answer? We were asked to draw cis, and it looks like one's equatorial, one's axial. Does that not matter? I mean, it's like...
Okay. We were asked to draw cis 1,2-dimethyl cyclohexane. Did we? Methyl at position 1, methyl at position 2. Are they on the same side? They're both aimed down. Did I draw cis 1,2-dimethyl cyclohexane?
Yes.
Yes. What else was I asked to draw?
The lowest energy.
The lowest energy. Did I draw the lowest energy for this structure?
Yeah. Yes.
And we will get a mix of answers with this. And I would argue the easiest way to solve that would be draw the chair flip. And I see people wincing, yeah? Okay. Right now, the easiest answer is to draw the chair flip because you need to internalize why these things are the way they are. If you don't go through and draw and just start jumping to answers, you're literally riding on a coin flip. Okay? A 50-50. When it's one question, 50-50, those odds aren't horrible, but usually we're stringing together multiple 50-50 questions. Your odds go down. Okay? And let's just take the 50-50 at face value. How many of you are going to be happy with a 50% on the final? Okay? So just saying, well, I'm okay with that, you probably actually aren't. Okay? Sometimes we got to deal with a little bit of harsh truth. Okay. So if we go through and do the chair flip, here's my feet. Which atom should be orange in my new structure?
The right nose carbon.
So we'll start here.
Yeah.
Left? There's nothing to the left. Tell me to go left. Am I hot or cold? Cold. Good answer. Colder?
Warmer.
Warmer by definition, right?
warmer.
Same warmness.
Warmer. Equal warmness. Ding ding, we have a winner.
That's the atom. As I go through that chair flip, what happens?
Your axial carbon becomes an equatorial carbon.
My axial becomes equatorial. There's my CH3. There's my H. Where's the red atom?
One carbon, right?
One carbon to the left. Going counterclockwise, it's back here. Okay, we'll have our axial. Sometimes you'll see a little break in the middle there. And the equatorial. What happened? The methyl CH3 and H. We've now done the chair flip appropriately. Which of these two chairs is more stable?
Neither.
They're the same. So in this case, it's kind of a pseudo backwards question because you look at it and have to draw them both out and find out they're both equal, which means I drew it and then spent all that time drawing an extra structure that I didn't need to because I actually had the answer. Okay? Kind of, sort of. How do I know they're equal?
You've got an axial and an equatorial.
Axial bad, equatorial good. Axial bad, equatorial good. I get the same balance in both structures. They're both equivalent energies. It didn't matter which one I drew.
It's because,
Go ahead, that's fine.
I
Go.
was going to say it's because they're the same size. It's because they're the same.
At this point, it's not just because they're the same size. It's because they have equivalent interactions in both cases. Okay? So I would argue it's not necessarily a size yet. It's equivalent interactions. There's an equivalent axial in both cases. There's an equivalent equatorial in both cases. And it doesn't have to be the same thing. That can complicate things.
So how do we know that is a cis?
How do we know this is a cis? Because that's a good point. Does everybody see in the overhead view that that is cis?
Yes.
Yes. Did I draw the correct chair for that?
Yeah. Yeah.
Where are those methyls aimed? Where are these methyls aimed? Does anybody want to append their answer to this being the correct drawing?
This is not the correct drawing.
All right. So, subtle issue. I didn't really notice it. Actually, I know why this happened. I was going to start at the other end of the structure. You guys said to start at the right-hand side of the structure, which meant I mismatched those. So what could we quickly do to fix this? The overhead? Because the overhead's going to be a lot easier to fix.
Dash them.
Okay. Okay. So are chairs still cis? Well, this one's down and that one's down, right? The CH3, down. They're both down. That's still cis. How about with this one? What happened? CH3 is down, down. What would my overhead view look like? Well, the CH3 was down. And if I go counterclockwise back, there's that one. Right? Everybody agree? What's the difference between my overhead views? They're the same. Does the overhead view show me energies? No. The overhead view hides all aspects of energy, which makes the overhead view a very questionable structure to use when looking at energetics for cyclohexanes. You can draw a Newman projection and convert it to the chair or to an overhead. That's fine. Okay? But be leery of looking at an overhead view as an example for energies. Kind of makes sense? Okay, so these were equal in energy, so that's kind of boring. Let's make it more challenging. Do the next one, cis 1,3. Where are you guys? How are you guys doing with it? Okay, so what we've got up on the board with the colored ones were my answers or my swing throughs of the. Okay, so we've got our cis 1-3, red and blue. I would drew them both up. Typically, I tend to go off of the point and not off this edge here. But if I went off the point, my equatorial would have aimed down, and I wanted it to match that, so I had to go up. So I had to switch to a different point to get the equatorial aimed up. Okay. If we look, we're going clockwise around. So I had to go clockwise around this, which I oftentimes screw up, but I think I did it right here. We're moving clockwise around the ring. There's that methyl aimed up. If I do the chair flip, we get the result over here. Do we see differences between those structures? Yes. And one, they're two equatorials. The other, they're two axials. Is there a difference in energy? Which one's the better chair? The one on the left. And that becomes the answer. Make sense? Okay. So one of your colleagues was brave enough to volunteer their potential answers. And so what they drew, I'm not sure I wanted to erase that. Oh well, already did. Okay. They drew the first one, and then they drew the second. Okay. I would argue drawing that first one was probably the easiest to go through and do, because they drew the axials. The axials tend to be easier to identify as up and down, and so they could nail that one down as our 1,3 dimethyl and cis. So everything looks good. Okay. They recognized that they were axial, and that was bad, so they wanted to go through and do a chair flip. Did they draw a chair flip?
Yes.
Did they draw only a chair flip?
No.
No. What they did was a chair flip and a rotation of the structure. Chair flip, yes, we've got equatorials now, so that's fantastic. But instead of doing just a chair flip, they did the chair flip and rotated the structure. Okay? This case didn't really matter. Chapter 5, that becomes incredibly important, to not do multiple permutations in a single drawing. So if you're going to go through and attempt to do these things, try to make sure you're only doing one permutation per drawing. The more permutations you stuff into a single drawing, the more likely you are to make a mistake, and those mistakes are not easy to find. All right? So the proper chair flip for this so there's my chair, head, equatorial, and equatorial. If you take that structure and now turn it by, it looks like 120 degrees on the axis running through the middle of the structure, you would get the bottom drawing. Okay? So you did a chair flip and a rotation. This case, it didn't matter, so you get me kind of, being like, yeah, you're right, but you could easily have screwed something up. So be careful with that. Okay? One of the things that I would caution you against doing is students look at this, well, it was 1-2 and it was unequal, 1-3 and they were equal, and we had one. So that must mean 1-3s are always more stable than 1-2s. No, because we could be cis versus trans. You're riding on coin flips. Okay? Until you've tested all possible permutations, be very careful jumping to conclusions. Okay? Just be aware of that. Kind of makes sense? Okay. With all of these examples, these were all just the exact same substituent. And ultimately, all we were trying to do was to get that substituent as much space as possible. Why did we want to give it as much space as possible? What made the substituent so special that it had to be equatorial instead of axial? Why is methyl so special? In comparison to what? To hydrogen. We're ultimately comparing this back to the standard structure, which had no substituents on it. Carbon is different than hydrogen because carbon has more electrons. Those more electrons need more space. What if instead of it being just a methyl, I went through and made it a T-butyl? Now these groups are different sizes. Okay? Are they both going to have an equal desire to be equatorial? No. Which one's going to have a larger desire to be equatorial? The T-butyl, because more electrons. So you always want to put your largest group as equatorial as possible to minimize those energetic interactions. Okay? And the statement always is dicey because we can find examples to force it the other direction, but we usually have to actually calculate energetics, and that's not worth doing in my opinion. Okay? So, next kind of topics that come out of this chapter, we have the 2D overhead, which gives us up and downs, nice and easy to see cis and trans. We get chairs, which are nice, kind of a 3D side view. This allows us to see axial and equatorial pretty cleanly. We get the Newman projection, which is also a 3D end-on view that really emphasizes the energetics. Okay? I would argue that the Newman projection is really just a tool to allow us to say that axial is high energy and equatorial is low energy. Once we've established that, when should we draw the Newman projection? How many of you do not want to draw a Newman projection? Only half the class. The other half was like, yeah, let me draw Newman projections. Okay? That's the only time we need a Newman projection, is to prove that statement. Axial is high, equatorial is low. We don't need to draw them ever again. We've got the answer right there. That's the answer. The Newman projection is the work behind it. So the chair Newman projection, we really don't ever have to draw again unless someone was kind of a dick and put it in an exam. Look at the practice exam. Right? The next fun one that comes out is the Haworth, which is a really... It's what biologists use to describe chemistry. Okay? We boil it down to the very nuts and bolts and try and ignore as much as possible about the actual three-dimensional representation because shapes are confusing. There's some phosphate buffer in the labs. For the burn? Never mind. 2D side view. We take our ring, and instead of looking at it from the top, we turn it on edge, which means we get this kind of side angle view that we're getting with the chair. But now, instead of seeing wedges and dashes, we have ups and downs to reference the wedges and dashes. Okay, why? I don't know, because somebody thought it looked cool, and that's how they drew it. Okay, but that's another representation of chairs. You get your Haworth projection. Okay, where this typically comes up is biochemistry or biology. What are we seeing here?
Fructose.
Since nobody knows the answer, I can just say it, and then no one can correct me. I believe this is actually sucrose. Okay, it's glucose and fructose. Yeah?
I think I'm pretty sure that's right.
I think I might be right.
It is right.
Okay? And so what we're looking at is the side view of it. Why might we switch to a Haworth instead of drawing a chair? Do you really want to try drawing a chair of that?
No.
Okay, no, that's hard to draw. Do you need to draw a chair of it?
Probably not.
Depends on the question asked. Okay? Most of the time you can get through biochemistry ignoring the chair conformations and you just memorize some extra nomenclature. See how this oxygen is aimed downwards? That one's alpha. If it's aimed upwards, it's beta. See how that one's aimed upwards? Well, that's D. If it had been downwards, it would have been L. And we go through these stupid memorization devices, and that expression exactly. It all comes from looking at the chair conformation. When you talk about the reactivity of the variety of sugars, okay, cell walls versus energy storage. Any biologists? Biochemists? Cell wall versus energy storage, fats. Guess what molecule they're made of? The exact same molecule. Do they have different functions?
Yes.
Yeah. Imagine if fat acted like a cell wall. If you think about it, when do cell walls degrade? They don't. It's kind of the point. It's why they stay rigid. If your fat was a cell wall, it's going to be hard to actually deal with. Fats are designed to actually process, which means there's a higher energy conformation of that molecule. What? Yeah. One of them we call alpha, the other one we call beta. Okay? They're there because they're different chair conformations. That's it. Okay? So, sort of not, they're here, one of those two. Text topics, things that you should go through and review on your own. Strain, the energy, you can look at the numbers and deal with that. Hey, there's that list of random names that you could attach before strain. Not a huge issue to know those, but I do at least want you to have read about them and seen them. Your cycloalkanes, you have propane, cyclo, prop, bute, pent. Okay, what are those relative shapes? A lot of that I feel is kind of self-explanatory, not a big deal. You should be working with models. The textbook provides a section on how to work with models and try and represent those different things. Okay, that's why we have the model lab as well. And then we encounter this fun one, IHD, which I've never heard it referenced like that until I read the textbook. The index of hydrogen deficiency, I've always heard it referenced as the degree of unsaturation. Okay? This is something that you can get useful information out of. I tend to ignore it because when it appears or where it appears is relatively minimal and not worth the time for me to learn a whole bunch about it. Okay? There's really two approaches. Number one, you're looking at a structure and you can come up with the index of pen. Thank you. Not index of pens. If you're looking at a structure, you can count your degrees of unsaturation by just counting how many rings or pi bonds are in the structure. So for that structure, I have 4 degrees of unsaturation. All right, that's it. There's 1 ring, 3 pi bonds, 4 degrees. Okay? The other way is this thing, okay, which, believe it or not, I derive every time I'm forced to use it. Okay? I have never spent any time memorizing because I think it's dumb. Okay? There are plenty of teachers that push it. There's useful information there. I just don't find it that useful. In that case, what you're given is the formula. C6H6. Okay? How many carbons? 6, so that would be 12 plus 2 plus how many nitrogens? 0. How many halogens? 0 minus the number of hydrogens? 6.
7.
Shit, seriously? That doesn't make any sense. 12 plus 2 is 14. Minus 6 is 8 divided by 2 equals, like I said, but not to belabor the point too much, 1, 2, 3, 4, 5, 6 carbons. Each of those carbons has 3 bonds shown, which means there's a 4th implied bond for each of them to a hydrogen. 6 carbons, 6 hydrogen, 4 degrees of unsaturation, C6H6. 4 degrees of unsaturation. That's why I was pausing when someone said 7. I'm like, that math isn't adding up right. Okay? That's what it's referencing. Okay? So depending on what you're trying to do, you might go through and do that. I do think it's important to evaluate the structure. I don't think it's important to evaluate the formula. We've already kind of addressed that. I don't like formulas. They hide way too much information. It's not worth the trouble to look at a formula. It is very useful to look at a structure to determine the index of unsaturation. Okay? Kind of makes sense? Okay. So, this is a fun, exciting chapter. Okay? And really all this is coming down to, if we boil it down to the very bare minimum, is your left and right hand. That's it. Okay? So if we go through the definitions we talked about, okay, do they all have the same pieces? My left and right hand. Yep, 4 fingers, 1 thumb. Are they all connected to like the palm of my hand? Well, yeah, so everything seems to match up. Are they superimposable? I am being a dick. Are they superimposable? No. Okay? And you're like, but I can't see the other hand. That's true. But remember, everything must occupy the same space. When I do that, the palm of my right hand is occupying the back of my left hand. Those are not superimposable. Okay? And you're like, God, that's literally with things that you've been living with for the last 20 plus years of your life, and you're confused. Okay? In like a week, you're supposed to figure this out with structures that you've now been talking about for 5 weeks. Okay? It is an exceptionally difficult concept to wrap our heads around. It is so vastly important that when it was first discovered, we effectively ignored it. Right? And said it was irrelevant. We didn't need to worry about it. So we aren't going to stress about this issue until they created a drug, thalidomide, which was a phenomenal drug at curing morning sickness. That little squiggle there is because that squiggle is a right and left hand. Okay? What that squiggle means is that could be a wedge or it could have been a dash. Well, the chemist that went through and did this was like, well, yeah, those are different. That's like my right and left hand, but like that's not that big a deal. And so they gave it out and it cured morning sickness, and it was a phenomenal drug at that. 10 months later, 9 gestation periods, you spit out a baby, and I know you don't spit out a baby, just for a record. Not a biologist, but I know that one.
Birth defects.
Birth defects. Okay? The big term that came out, not the nicest term, but this was super, super common, flipper babies. Because it made massive deformities to external limbs. Okay? And kids end up being born with flippers instead of arms. They didn't get the actual dexterity to build fingers. And they were able to eventually trace it back to the other form of the drug. And it was kind of the sole cause behind this. Okay? So it makes a really big difference. But being able to acknowledge its importance and being able to see it become an entirely separate issue. And that's where Chapter 5 comes in, is really trying to force you to look at model kits and look at those representations to really lock down their independent meanings so that you can see those differences. Okay? It is exceptionally difficult to do. Okay? More than any other chapter, I feel this chapter makes me look like an idiot. Okay? And that's because I've come up with coping mechanisms to deal with the pain of this section. Because I have a very hard time manipulating these structures. Okay? Even after 17 years of working with it, I still go through these hard kind of redraw everything. I want to do a rotation, I'm going to draw that rotation. But I know I need to do 4 rotations, I'm drawing 4 independent structures so that I don't screw it up. Because I have found that if I don't do that, I do screw it up. Okay? This is a 50-50. Okay? This whole chapter rides on 50-50s, and most every question stacks multiple pieces into them. Okay? So the odds of just guessing get really, really slim. Unfortunately, the odds of just guessing in the homework aren't so slim. So this chapter seems to create this false sense of, oh, I totally get it. That one's totally the right hand. When all you're given is right and left hands, half the time you're right. And it turns out half the time you're right is in the homework. you actually don't have any fundamental understanding of what's actually happening, and you screw it up all on the exam. It's just what I've seen. Okay? So be careful with this. Really, really make sure that you know exactly why something is happening or what the labeling needs to be. Not just, well, I think it should be wedged because my instinct is saying it's wedged. Okay? That is difficult, but please watch out for that. Okay? So, the big term that comes out of this is this difference between chiral and achiral. Okay? Chiral is if it's non-superimposable on its mirror image. Okay? Remember the whole left and right? Oh, they totally overlap. Careful. Okay? What we're talking about is non-superimposable on its mirror image. So if we did a mirror image, if I take the right hand and do a mirror image, what does it look like? It looks like the left hand. The mirror's running right through the middle here, and I'm just reflecting across. Did I have to reflect across right through the middle of me? Is that still a valid mirror?
Yes.
Okay. Your mirror plane can show up anywhere. That's one of the other things that complicates things, is depending on what you see for your mirror line, may make it more difficult for somebody else to interpret what's going on. So you'll see me slow down a lot within this section when working with individual students to really nail down exactly where you're saying your mirror is before we draw. Right? So that I know what you're trying to do. Okay? Once we have that mirror image, now it's a question of, can it superimpose? Well, when we took the left and the right hand, we just go, oh, well, they don't superimpose. But remember, what else do we have to do? You have to be able to flip the structure, okay? Turn them, rotate them, because maybe they aren't going to perfectly align right away, but if you did a rotation, maybe it does align, okay? So you have to be aware of all those extra permutations that you did in Chapter 4 to understand those structures, okay? Achiral, okay, is if it is superimposable on its mirror image. Okay, so the examples we use for chiral are your right and left hands. They're not superimposable. But if we took a chair and reflect the chair, and we mirror image the chair out, are the chairs mirror images? Yes. Are they superimposable? Yes, because I can now pick this up and put it on there. Okay? Kind of makes sense? Okay. Scissors. Any lefties in the room? Oh, there's a lefty. What do you think about scissors? Scissors are hard. Why are scissors hard? What do you think about scissors? Scissors are chiral. They're designed to match your right and left hands. Since your right and left hands are chiral, guess what scissors are? Chiral, which is why lefties hate righties, right? Because they invent all these stupid tools like scissors that only function for right-handed people, right? So we have to be kind of aware of these mismatches because it makes a big deal when we get to our structures, okay? So here's our flow chart that we saw before, okay? This stereoisomers is really where we're going to get this new category for our chiral molecules. Take a look at the two top structures above. What do you think? Do they have the same molecular formula?
Yes.
Yes. Okay. Are they superimposable?
No.
You're like, well, 4 carbons and wedged. It must be true. Okay. If we take that rightmost structure and we tried to overlay it, let's see if I can do this right. It would do something like this. Okay, well, that doesn't superimpose, but you're like, well, duh, you idiot. You flip the structure. Okay, so if we flip it, right, now it would superimpose. The chlorine was aimed outwards. If I flip the structure,
Inward.
I change its orientation and it is now dashed. Do the chlorines superimpose? No. Those two structures are stereoisomers of each other. Okay? That molecule would be chiral. It is non-superimposable on its mirror image. So let's take a real quick, mirrors are blue, right? So there we go, blue mirror. Or they're black, right? Sorry.
Chiral.
Stereoisomers are achiral.
Okay.
Right? Everybody see that's the mirror image in black? Okay. No? Is there a no or a yes? Are we good?
Yes.
Yes? If we take that structure, you notice it doesn't align with the carbon backbone, so we'd have to take it and flip it over so the carbon backbone aligns. The chlorine is aimed at you, and I flip the structure over. It's now aimed away, and it doesn't superimpose. It is non-superimposable on its mirror image. Not easy. It takes practice to deal with these. You need that practice. Okay? With that, we're going to have to